All right, this is Peter with CalcBook, and today we're going to be talking about flexural design of single angles. So one of the biggest things to understand about single angles in flexure is the difference between geometric and principal axis bending. So when we talk about geometric axis bending, right, we talk about bending that shape about its geometric axes. This typically happens when you have bracing along the full entire length of the angle, which allows it to bend about its geometric axis. On the other hand, we have principal axis bending. When you have an unbraced angle where the compression flange is not braced, the angle actually rotates during flexure, and you have to evaluate the angle about each of its principal axes, so MZ and MW. What affects the moment capacity of single angles? So we look at the different things, right? We talked about whether you're looking at the geometric axes or the principal axes, right? So braced or unbraced. Obviously the angle size, thickness, material properties. And then as well as the applied moment, right? So that comes out in our CB factor. So for a distributed load, you're going to have less capacity. For a point load, you're going to have more capacity. So let's go ahead and take a look at an example problem. So we're going to be looking at an L 6 by 6 by 1/2. We're going to have an unbraced length of 10 feet. This is going to be completely unbraced. And then we have an ultimate moment of 9 kip feet, which comes from a distributed dead load. So we're going to be verifying the capacity of this beam for LRFD design. So let's go ahead and open up CalcBook. All right, so we're going to go ahead and click into our steel design. We're going to go ahead and do a steel member design, and then we're going to go with our steel member module. And then we're going to go ahead and click on flexural major axis. Now, for single angles, it's all going to be in one module, so whether you click minor or major, it will go automatically into the same place. So we're going to go ahead and select our shape, which is going to be a single angle, and it's going to be an L 6 by 6 by 1/2. And we can see that the properties there for Fy and Fu are already populated, so we're going to go ahead and leave those as is. And then we can go ahead and click into our flexural design. And you can see that it's already opened up the chapter H combined loading, because ultimately that's what we're going to have to use to find the capacity of the single angle. So our bracing configuration for this problem is going to be unbraced. We're going to enter our length, which is going to be the full 10 feet. And then our CB factor, we can go ahead and click in. Right, we've got a distributed load like this with no bracing on it. So we're going to use a 1.14. And then for our demands, right, we just have a dead load. And we added these information buttons here for bending about single angles. We can be a little bit complicated. So you want to make sure that you're following the sign conventions that we've laid out here. So loading in the down direction when the angle is shaped like this is going to result in a positive moment that you're going to enter. So we're going to go ahead and enter in our positive moment of 9 kip feet for dead, and that's all we have. So now we can go into our calculations here. For the flexural demands about each of the geometric axes, that's just going to be our applied dead load times the load combination for the controlling, which is going to be 1.4 times dead. And then for the y-axis, we don't have anything, so that's going to be 0. And then we have to transform those loads about the principal axes. So we do have a little bit of sign convention to take care of, so we multiply that moment about the x-axis by -1, and then we find the demand about the major principal axis, MW, which is going to be -8.91 kip feet. And then even though we don't have any bending about the y geometric axis, we still get bending about the z principal axis because of the rotation from the moment about the x-axis. And because it's going to be an equal angle, it's going to be the same moment, just a different sign convention. So then we go and check our flexural strength about the principal axes. So we look at the w-axis first, right? We look at our moment strength due to yielding. Then we go into our moment strength due to lateral torsional buckling, right? So we have lots of complicated equations here. It's all taken care of by CalcBook. And we look at the local leg buckling, right? For this one, the leg 1 is in tension, so there is no buckling. For leg 2, it's compact, so the leg buckling does not apply. So our design flexural strength is controlled by lateral torsional buckling of 27.75 kip feet. Now we go to the z principal axis, and again we check our moment strength due to yielding. We check the local leg buckling, which the leg is compact, so it doesn't apply. And since it's an equal angle, both legs are compact, so it does not apply for leg 2 either. And then we have a capacity about the minor principal axis of 13.85 kip feet. And now we go over to our combined loading tab, where the information's already been brought over from our other tabs. And we find that we have a DCR combined loading of 0.96, so we're acceptable. This is CalcBook with Single Angle Flexural Design.